first, you note that it's kind of strange problem with no obvious solution. So what you do is you forget about this problem and you take a simpler one. Instead of having a two-dimensional grid, you take a one-dimensional grid. So suppose that you have some very abstract collection of beads, and you're given some beads here, some beads here, and you're given that this point here is optimal. Suppose that there are no beads here at this point. And suppose that you look at the points to the right, just to the right of it and just to the left of it. What you can show is that these points are going to require the same number of moves as this point, so they're also optimal. You do this because the number of beads that you move to this point to the right of it, so here, and the number of beads that you move to this point to the left of it are going to be equal. Otherwise it would not be optimal, and you would be able to find a smaller number of moves by looking at the point to the left of it, say if L were greater than R, because there would be more points here than here, and the number of moves to move all of them to this point, which is closer to the left, is going to be less than the number of moves to move them to this point. And since you're given that this point is optimal, you say that L must be equal to R. And this means that up until the first point to the left where there is a bead, all these points are going to be optimal. And the same on the right. So this is the first bead on the right, and all these points are optimal. And this means that in 1D, all you need to do is, instead of considering all possible points which you can use to move M beads to them, you only need to consider the points at which there is already at least one bead. And in the conditions of the problem, there are fewer such points, because the largest number of such points that you can have is the number of beads, and it cannot be too large. And this solves the problem in 1D because this is very easy to implement. You say that x, you define the set of all coordinates of beads, and you say that for x in x, find the minimum. For it, you say that R is equal to infinity, and for x and x, you say that R is equal to minimum of R and number of moves to x. And this is easy to implement because the set x is small. And that is in 1D. In 2D, what you do is you notice that if you have an optimal point on a grid somewhere, then the problem splits into two. First, you move all the beads to this line, to the line y equal to, say, y. This will be point x star y star. You first of all you move all points to the line y equals y star, and then on this line you move all points to the point x equals x star, which is this line here. And this suggests that the problem in 2D is roughly the same as the problem in 1D, in the sense that all the points y star that you ever need to look at are the y coordinates where there is already at least one bead on this line. And so you would show that if you have some lines here, and you know that the optimal point lies on this line, then there is at least one other bead on this line, and the same goes for this line. There is at least one bead on this line. And this means that you define the x to be the all x coordinates of beads, and y to be all y coordinates, And the solution is to look at the minimum overall x in x and y in y of the number of moves to move m beads to xy. And that is the correct solution of the problem.